time with a schedule that reduces the steps.
Morning, everyone. It's still morning in the States. I know it's afternoon in Italy. First, I want to take a bit of time to thank the organizers for inviting me to this interesting workshop. I would really have liked to be there in person and meet many of you. With that, I'm going to go and talk a little bit about the work we've explored in this direction, and in particular, the focus for myself and the group of collaborators from the University of Maryland, which I listed here, some people contributing at different stages in their life on this project, is about trying to use this machine learning techniques for theories with fermions. So, see, I'm going to talk very briefly about how to do configuration sampling using machine learning. The toy problem and the toy approach we're going to use for this is a restricted Boltzmann machine as a proposer, and describe that with a little bit of details. And then I will move to describe the fermion estimators that are needed to implement this for QFTs, quantum field theories with fermions, and show this in the context of an example, in this case, the massive Turing model, at least as regularized on the lattice. And then I'll finish with the summary and outlook. So the idea is the following. So we have many interesting quantum field theories that can be studied in the non-perturbative regime using Monte Carlo methods. The approach that I'm going to use here is for quantum field theories that are regularized using a lattice cutoff. By that, we mean that for people that are not practitioners, we actually sample the quantum fields on a grid of points and describe the problem using a large dimensional integral. In Euclidean framework, this problem is equivalent often with the statistical mechanics problem. There are exceptions to this, but the focus here will be on theories where this is the case. So in particular, the probability of a particular field configuration to occur in our sample is driven by a Boltzmann factor that it's real and positive. Often the sampling of this is numerically difficult, either because the action is expensive, for example, when you have fermionic determinants, or maybe the action is multimodal, and so all sorts of difficulties can arise. And there is a hope that some of these problems can be overcome using machine learning techniques to sample the space of configurations. So, as I said earlier on, the field of configuration is described by many real numbers, each of them associated with the grid, or many at one grid point. And then the action, I'm writing here a schematic action, one of the simpler actions that you can have, that describes the Boltzmann factor and plays the role of maybe what energy is for people that are familiar with thermal statistical physics. The action is some polynomial usually in these fields. So how to use machine learning for this? The idea would be to use a generative model for machine learning. What you want to do is use a numerical chip method to generate configurations. Of course, the configurations are dependent on the particular model, machine learning model you're using. And generically in this talk, I'm going to refer to the probability of generating configurations from the machine learning model as pi of phi. For this to be useful to us, this approximation, this probability distribution in the machine learning thing has to be somehow approximatively equal, or to a good approximation equal with the probability distribution that we want in the quantum field theory. And the idea would be then to take a model that can be trained to generate good approximations of this probability distribution. Of course, if we're going to just then use the trained model to do the sampling and then evaluate our averages, these approximations will introduce some bias, and this has to be corrected. Then, on the next slide, I'll discuss how this is to be corrected. And of course, you can use any generative method from the machine learning to generate this underlying distributions. There are a number of things that have already been basically employed for QFTs. There's a group at MIT, Fiala and collaborators, have used this idea of normalizing maps, where you do, basically you do Gaussian distributed fields that can be easily generated, and then you push them through a map. It's in the Jacobian of the map that the QFT non-trivial parts are being encoded, and basically the training is done by adjusting the parameters of the map. There is the restrictive Boltzmann machine that I'll discuss a little bit today. And of course, there are other things more afield, akin to the things that we'll discuss just earlier. We used, for example, machine learning techniques to do path deformations, and that was in the context of trying to simulate QFTs that have a sign problem. Now, with that being said, how do we do bias correction? Bias correction, it's usually done using this so-called Metropolis Hastings accept reject step. So if you have, I'm giving here an example, a bit of a cartoon, if you have a particular probability distribution that you want, for example, coming from QFT, and if you have a probability distribution for the fields that comes from your machine learning method, what you can do is use the machine learning method as a proposer. So you propose a new configurations with the probability, characterized by the machine, and then you accept or reject the new configurations based on this probability distribution, which involves a ratio of the probability distribution, so a relative probability of the true distribution and the relative probability of the machine learning method. And if you do this, then the PDF will actually be statistically the same, and in principle you can recover the results you want, and presumably cheaply. For this method to actually be efficient, we need a few things. So the first thing is generating a new field from the machine learning method should be cheap, because otherwise it defeats the purpose. The second thing that you need is to have a way to calculate the relative probability associated with the machine learning model efficiently. You need also to be able to compute this relative probability of the QFT efficiently, and then the probability distribution of the ML should be a good approximation of the probability distribution of the QFT. One way to look at it, and I'm plotting it here, is to look at the how well the probability on the ML machine tracks the probability in the QFT. So in particular, you want this divergence or tension between the machine learning and the QFT probabilities to be small when you sample this over the important configurations. So here I'm showing, how these things track each other, the fluctuations in log pi and the fluctuation in log p. In this particular case, where the distributions don't match very well, and as you see, instead of being completely on this line, they deviate a little bit. Of course, deviations are expected, but one thing to keep in mind is that these deviations, cannot be much larger than one, otherwise the probability distribution, sorry, the probability of acceptance of this Metropolis-Hastings step drops down and the efficiency of the method vanishes. And so it's important to keep this in mind, because these quantities that appear here are actually extensive, so they actually grow with the volume of the configuration that you're trying to study, but the tension between them should stay of the order 1. So it cannot just track percentually. It has to be, the difference has to be of the order 1 for this to work. Now, one thing in particular that is problematic for theories with fermions, or for quantum field theories with fermion, is that computing the relative probability of the QFT is not numerically cheap. It involves calculating ratio of determinants, which is expensive. So the focus here would be how to overcome this kind of problems in theories with fermions, where this ratio of probabilities cannot be computed, at least cheaply. So to introduce this, I'm going to talk about a particular restricted Boltzmann machine. That's one generative model based on ideas from the machine learning community. The logic is the following. You have the so-called visible nodes. In this case, our visible nodes are actually just sites on the lattice, so the fields evaluated at every lattice point. These visible nodes are augmented with a set of hidden nodes, which again, this is just a topography of things. We can actually imagine that, these hidden nodes actually store their own values. And then you introduce an energy function that couples the visible nodes to the hidden nodes. And the energy function is introduced and designed in such a way that you can actually sample this joint probability between the hidden nodes and the visible nodes easily. So in particular, the reason we call this restrictive Boltzmann machine is because there are no couplings that involve the visible nodes with themselves or the hidden nodes with themselves, and that will add in the way we do the sampling. The way we generate new fields phi with this machine, assuming that we have it all trained, is that we first generate a value of hidden nodes while keeping the visible nodes fixed. So we do this, we need this conditional probability somehow evaluated, and we need a method that allows us to sample the field's age when given a certain set of visible nodes. And then the reciprocal thing, you fix the values of the hidden nodes, and then you need to sample the value of the visible nodes with this within a context of a certain value for the hidden node. So you alternate between that. First, you generate values for hidden nodes, then for visible nodes, and then you can repeat the process. Usually, this process decorrelates very quickly, so it's very rapid that you can generate new set of fields phi that are decorrelated from the ones that you started. You only need to take only a couple of Gibbs alternation steps. So this whole process can be made fast if you can sample the conditional probabilities effectively. So you really need to be able to sample the hidden nodes quickly and the visible nodes quickly when the other ones stay frozen. To train this restrictive Boltzmann machine, what you have to do is fiddle with the parameters that appear in the energy functional. The parameters that appear in the energy functional are, for the main part, not all of them, we'll see the exact example a little bit later on. For the main part, the couplings between the visible and the hidden nodes, and there are, obviously many couplings of this nature. If you have volume number of visible nodes, then it will be volume times the number of the hidden nodes, number of couplings here, that all have to be trained. The training is what it's called a supervised training. you generate a set of configurations for the visible nodes by some other method that are drawn from the probability distribution that you desire, the QFT probability distribution. Now, this in itself can be a bottleneck. And then you train the RBM so that you can actually produce with the RBM a good approximation pi of phi to the QFT probability distribution. Now, the training is done by evaluating the so-called Kullback-Leibler divergence. I'm sure you've heard this several times this week. And the idea would be to adjust the parameters of the energy function of the network, here in such a way that this divergence is minimized. And I'll discuss a bit more details once I spell out what the specific form of the energy function is. So to make things a bit more specific, I need to lay down the toy model that we're going to play with, and that's a massive Turing model in 1+1 dimension. This is a model that was introduced a long time ago, and some limits as a solvable case, in the continuum. It's still a model that has interest even today's in 2+1 dimensions. There is a lot of interest in establishing the various phases of this model depending on the number of flavors you have in the model. We're going to use only a lattice discretization of this model and not really pursue this in the continuum, and we're going to do it in 1+1 dimension where the calculations can be done reasonably cheaply. The Lagrangian density for this model describes basically a set of NF number of flavors, fermions of mass m, that are coupled with this vector-vector interactions, and the strength of the coupling is given by this parameter g squared. Now, in order to actually do numerical simulations with this, the usual techniques apply. We have a quartic fermion interaction here, so this has to be reduced to something quadratic, and the way it's reduced with quadratic is via Hubbard-Stratanovich transformation. So we introduce this auxiliary field phi's and reduce this Lagrangian density to an action that involves the auxiliary fields, and then the fermionic fields, the one that we're interested in, are basically appear only as a quadratic form. The advantage is that this quadratic form can be actually integrated exactly, so you don't have to represent Grassmann fields in the on the computer. And when you integrate them exactly, the fermionic contribution actually becomes determinant, and this is the so-called fermionic determinant, which is a function of the auxiliary field phi's. So we're going to end up with a pure bosonic piece of the action, which involves only the auxiliary field, and there is a fermionic piece that involves the determinant of the fermions. To be specific, we use this particular discretization where the field phi's are actually compact. The reason we use compact fields is mostly historical. We're more familiar with using compact fields from our studies of contour deformation in the context of this model. The fermionic part can be discretized in a number of ways, and for the things that I'm going to discuss today, we use Wilson fermion discretization for this, and we're going to use two flavors, because this way the action is guaranteed to be real, and the probability, the Boltzmann factor, is real and positive, so you can really think of this as a statistical mechanics problem. Now, there are two parameters that appear in this action: is the mass of the fermions and the strength of the coupling. In terms of this lattice action, we choose the strength of the coupling we set to 1, and the parameter kappa that it's related to the mass of the fermion is set to actually it's 0.285 that corresponds to a negative bare mass. The important thing is in this theory is, you're going to have fermions, and then you're going to have bound states of fermions that are bosonic. So you can actually measure what the bosonic states, the bound states are, and the fermionic states by looking at correlators. So you feed this correlator and you find that for this choice of parameters, the bosonic energy is in lattice units 0.44, and the fermion mass it's 0.3. The important thing is to note that at least in the non-interacting case, you would expect that the boson that involves two fermions would have the mass of twice the fermion mass. The fact that this is about 1.5, the fermion mass, tells you that you have a rather strong interaction. So we are in the a strong coupled regime. That's the whole point of these parameters here. So with this in hand, let me introduce the energy functional used for the restricted Boltzmann machine. So the energy functional is periodic in the auxiliary fields phi. At least we used it this way because the underlying probability distribution function from the QFT is periodic in phi. Maybe I didn't make this point. Let me go back for a second and point out that in the auxiliary field action, you have this periodic function of phi, and moreover, in the fermionic matrix that appears in the determinant expression, the auxiliary fields also appear in a periodic manner. So, since the field is periodic in the QFT probability distribution, we design an energy functional for the RBM that also is periodic. We couple basically the hidden nodes and the visible nodes using this W and W tilde coefficients. We couple the sign with the sign of the hidden nodes and the cosine of the visible with the sign of the hidden nodes using the W and W tilde. And similarly, we define some on-site parts of the action that involve, again, the sine and cosine of the visible nodes, and for the hidden nodes, just the sign. With this energy functional, we can actually compute, we can marginalize. This, of course, gives you the probability distribution for the visible and the hidden nodes, and you can marginalize with respect to the hidden nodes, and you get the relative probability that we will need for the visible nodes. And this expression, as you see, it's a product over sides of these particular functions. You can also evaluate the conditional probabilities, so this is the probability of the hidden nodes when the visible nodes are fixed. And similarly, the probability for the visible nodes when the hidden nodes are fixed, these conditional probabilities. And the relevant parameters that appear here are listed in these formulas here. But the most important thing to take home from here is that the conditional probabilities factorize completely over side. So all you have to do is figure out a way to sample, in this case, fields phi based on this probability distribution at every site. And similarly, in the other Gibbs alternation step, sample the fields age at every site separately. By the way, this probability distribution is known. It's called the von Mises probability distribution, and there are efficient methods to sample it at every site. So we can actually very quickly generate the hidden fields and the visible fields, in the Gibbs alternation. So what we have to do to train the RBM, we have to minimize the Kullback-Leibler divergence. For this, we use a stochastic steepest descent method, which seems to be the method of choice for this kind of problems. When you compute the gradient of this quantity, at least with the defined on the training set that you have, you see that you have a positive part and a negative term. The positive term is evaluated over the training set. So you just take an average over the training set. The negative term needs to be evaluated stochastically, and there is a method based on using the training set and doing a few Gibbs alternation to get a stochastic estimator for the so-called negative term. And then you just, based on this stochastic gradient, you just go in the direction that decreases the Kullback-Leibler divergence. I'm illustrating here on the right-hand side the behavior of the various parameters as a function of the training step. The machine learning community calls this an epoch. And as you see, I'm plotting, because these are many parameters, I'm plotting the norm of the matrix, and as you see, the norm of the W and the W tilde matrices stabilize at long term. And that's when, you reach at least the local minimum, because the gradient basically vanishes. It doesn't quite vanish because you really have a stochastic piece to it, but it goes very close to zero. So these are the various parameters that actually enter the restricted Boltzmann machine. And you see, this is the guy that stabilizes the latest. All the other guys stabilize actually quite early in the process. I should also mention that for this particular case, we can also look at the variance of the probability distribution of the Boltzmann machine compared to the QFT over the training set. So you can compute how much of a tension you have between the pi distribution and the p distribution over the training set, and hopefully this also gets minimized, and you can see that actually this also changes very rapidly and then stabilizes. We actually monitor this quantity to actually decide on a stopping criterion, but you can obviously place a stopping criterion based on the gradient of the Kullback-Leibler divergence too. So once you have this thing trained, you can then use the RBM to do sampling. The PDF for our quantum field theory has this auxiliary field part, the bosonic part, and then it has this fermionic part, which is the determinant. The determinant is not Hermitian. Sorry, I should say that the matrix is not Hermitian, but it has something that is akin to gamma 5 symmetry that ensures that the determinant is real. So the determinant square is actually positive, and it's a real and positive definite. And what you do, of course, you use the RBM as a proposer, and then you do an accept reject as a warm-up. We use an accept reject where we don't use an estimator for the determinant. We're using the determinant directly, and we can actually monitor what happens with the acceptance rate as a function of the volume of the lattice that we use. We used a single hidden node in our representation of the RBM. Of course, that could be made presumably better by increasing the complexity of the RBM. We found that if we use one or two nodes, things didn't change that dramatically. So really, we need to actually create a more complex implementation that allows for more hidden nodes to actually see that kind of improvement that we would want. But it's not really that important for the part of the thing that we were trying to study, which is the fermionic determinant. You see here the probability of acceptance on small lattices. It's actually quite high. It's more than 40%. And this has to do with the fact that the RBM actually is, the trained RBM can capture quite well the probability distribution of the quantum field theory. But as the volume increases, the probability of acceptance of the correction step decreases. So this introduces inefficiencies in the problem, and of course this can be fixed. But for our purposes, what we've done is to fix ourselves to a single point here in the, we use a 10 by 10 lattice where the performance of the accept reject step is about 25 to 30%. I mentioned that the performance decreases with the volume of the lattice, and this actually can be understood quite well by looking at the tension between the RBM probability function and the QFT probability function. And if you look at the variance, you find that the variance starts close to 1 on the smaller lattices, and it increases, not quite proportional with the volume, but it does increase as you go to larger and larger lattices. And as I said, you know, if you go away from 1, the probability of acceptance of the correction step drops quickly. So while the increase in this variance between the machine learning, the RBM, and the QFT is not large, going from a 6 by 6 to a 20 by 20, it's about a factor of 10 in the volume, whereas this thing grows from a little bit over 1 to a little bit over 3. The acceptance probability drops very quickly. So for you know, practical machine, we need to implement an RBM that it's better at keeping these things under control on large volume. But again, the focus here will be on the fermionic part of the action. So we chose to work on this 10 by 10 lattice for the things that I'm going to show you in the rest of the talk. So I mentioned earlier on, we need to actually compute the ratio of probabilities for 2 configurations, the proposed one and the old one, using the full lattice action that involves the ratio of the determinants. Just to set the scale here, while D is actually a sparse matrix, so most of the entries in it is 0, still the calculation of the determinant is proportional with the cube of the volume of the lattice. So it increases very quickly. So for large volumes, this will become a significant bottleneck. And so in order to avoid having to calculate this ratio of determinants, we plan to use an estimator for this determinant ratio. Now, care must be, you know, this estimator must be chosen very carefully. We're going to introduce here a matrix that is Hermitian and positive definite, because it'll help set up the estimator correctly. This matrix is simply d dagger d, and it has the property that the determinant of this omega matrix is the fermionic contribution to our probability density function. So we all care about getting an estimator basically for the determinant of this positive definite Hermitian matrix omega. There is a proposal from a long time ago due to Grady on how to use an estimator to correctly create an unbiased method. And the idea is to generate some sort of, in the accept reject step, instead of actually computing the ratio of determinants, what you do, you generate a random vector zeta with the probability that it's controlled by the matrix over the proposed fields. And then what you do, you compute the ratio of this part of the action, and then you can prove that this is actually satisfies the Taylor balance, and everything works very neatly. And what you do, how to generate zeta, because it seems like it's a bit difficult to generate zeta given that you want this particular probability distribution. It's not really that difficult. You generate eta, that it's a Gaussian field, and you know you can actually generate eta quite easily. There are easy techniques, and then zeta is set by solving this particular linear problem where omega here is the square root of, the inverse square root of the matrix omega evaluated over the proposed fields phi prime. Now, to evaluate this square root, you need omega to be positive definite, and that's why we've actually made this particular choice for omega. The problem is that if you actually use this estimator as it's written down, the probability of acceptance actually becomes 0 immediately. And to understand why that is, you look at this accept reject step and think of it as being driven by some sort of an effective action. So it is the fluctuations of this effective action that matter. If you look at the effective action, you can spell it out. There is fluctuations of the effective actions are driven by the fluctuations of the auxiliary field. There is a contribution that comes from the ratio of the probability for the field phi's that come from the machine, the RBM. And then there is this term that represents the estimator of the determinant ratio. Now, if you see here, the fluctuations over the auxiliary field, at least for a 10 by 10 lattice of the parameters we've chosen, are around 30, give or take another 10 or 15. They are very similar with the fluctuations of the second term, and they nearly cancel. You see, they're highly correlated. The problem is that this term, the estimator for the determinant, has enormously large fluctuations, and it drives basically the fluctuations of the effective actions, which are enormous, and basically no proposal is actually accepted. So how do we deal? What's the reason for this, and how to deal with this? We need to use an improved estimator. In particular, the fluctuations of this estimator, which produces the determinant ratio when you sample over eta fields. So I'm writing this estimator now directly in terms of these eta fields that are Gaussian. You need to reduce the fluctuations of this estimator. And it turns out that in this particular form, it's easy to actually figure out where the problem comes from. Although omega and omega prime are actually positive definite, this matrix that appears here that you need to construct, if it has eigenvalues that are smaller than 1/2, the variance of the estimator becomes infinite. And if you actually take this combination of matrices and look at the spectrum, you find that the top part of the spectrum, it's at about 50 or 60 with large excursions upwards. But more importantly, the part that you're interested in, the lower part of the spectrum, is, much lower than the 1/2, 0.5 limit, where this estimator ratio, the estimator of the determinant ratio has an infinite variance. So you have to figure out an estimator that doesn't violate this bound. This one does. No, all is lost. There are standard techniques to deal with this kind of problem. The only thing that you have to be careful is to figure out a way that keeps the algorithm exact. So in this particular approach we used is to break the matrix omega, take the nth root, and then apply it n times. The estimator that you construct out of this involves the nth root and the 2nth root of the inverse of these matrices. The advantage is that this is an unbiased estimator for what you need, and it works perfectly well as a replacement, and the algorithm remains, exact. And the improved estimator is n times more expensive than the original one, but the variance is decreased dramatically. So for example, if you take the problem that we just had, the same backgrounds, but you break this estimator into 8 pieces already. And I chose 8 here because, you know, I could tell that the 8th root would actually bring the estimator to have the right to almost not violate the bound. The bound is at 0.5. You see that at n equal 8, there are only a handful of cases where you have a violation of the bound. So, you know, presumably in your simulation, you would use breakup that it's a bit larger than 8. The matrix roots that appear in here are computed using a polynomial approximation over the spectrum of omega. That's a standard technique. I'm not going to discuss it here. And what you do then...
Andrei, sorry for the interruption. You have about 5 minutes.
Okay, thank you. What you do then, you know, you can use this, you know, improved estimator and replace it there and study what happens as you increase the breakup order. On a 10 by 10 lattice, as I mentioned, you know, the measured when you don't use an estimator, the acceptance rate is about a little bit less than 30%. So that's sort of, if you have a perfect estimator, you should see an acceptance rate that it's about 30%. And indeed, what happens as you increase the breakup level, the acceptance rate, you know, basically converges towards the one where you have no estimator. It actually, this curve can be fit for the, this curve can be actually understood perfectly in terms of the fluctuations of the estimator, and the fluctuations of the estimator as a function of the breakup order are controlled by an intrinsic piece, and this intrinsic piece basically corresponds to fluctuations of the ratios of the determinant, the exact ratios of the determinant over the auxiliary fields. And then there is the stochastic piece that gets reduced by n, as n being the breakup order. And I plot here on the lower part of the plot, I'm also plotting an observable, in this particular case, the action average, to show that, you know, at any breakup order, of course, you get an exact algorithm that produces the same value of the observable as computed. The bar here is computed with no estimator, and this is computed with different versions of this estimators, you know, different breakup levels. All of them produce the same value, but some are more efficient at moving through the configuration space than others. What's interesting is what happens if you increase the volume. I didn't have a direct access to the data to redo the whole study at different volumes, but I did have access to the variance of the intrinsic part of the estimator. So we expect that the breakup level would actually need to be increased as you increase the volume. A good rule of thumb, if at a particular volume you find a particular breakup level to be acceptable, as you increase the volume, you want to keep basically the fluctuations of the stochastic determinant fixed, and that would require basically to increase the breakup level proportional with the fluctuations of the stochastic determinant. We find, for example, the intrinsic part of the fluctuations to increase, you know, to our surprise, we expected that they increase actually with the volume. We'll find that they increase with at a rate that it's slightly larger than the square root of the volume. So, you know, something like 0.6, 0.7 of the volume. So if the stochastic estimator increases at a similar rate, then the cost of using the estimator asymptotically would go like power between 1.6 and 2. There is a power of V already in the calculations of the estimator, because all calculations are proportional with the volume. Multiplications of matrices that are sparse, it's only vector matrix multiplication are only proportional with the volume. So there is another factor of maybe a volume coming from the breakup level. In any case, we expect that asymptotically, this method would outperform the exact determinant calculation, since the exact determinant calculation actually scales the cubic volume. And that's pretty much all I wanted to talk about. So before I finish, I want to put a few things in front of you. Some conclusions that generative ML models can be used to sample PDFs for QFTs. And even if you only have an approximation, that's not the end of the world. If the approximation is good enough, you can actually remove any bias by doing an accept reject. However, for quantum field theories where you have fermions, practical algorithms will require to figure out a way to compute the determinant ratio efficiently. And most likely, you can use estimators to do this, but you have to figure out ways to keep the fluctuations under control. There are other possibilities, but that's the one that we explored. The estimator strategy I discussed is not RBM specific. So in principle, you can marry this either with an improved RBM or with, one of these, normalizing flow kind of proposals. So that's something to keep in mind. And obviously, the RBM that I played with here, it's actually not performing very well at large volumes. So, if you're interested in pushing at that direction, obviously, improvements for the RBM are required. So with this, I thank you for your attention, and I'm ready to answer some questions.
Thank you very much, Andrei. Other question? Oh, I can see. Yes, I can see certainly one by Julian.
Hi, can you hear me?
Yes, I can.
Thanks for the great talk. I have a few questions, but stop me if it takes too long. So you mentioned that you have a training set which you use to train with the Kullback-Leibler divergence, but can you not just sample from the model and use the reverse KL, so purely variationally without having a data set?
We did not explore this. I would have to actually look at the details and see exactly whether it's possible. I've seen it done in different contexts, so it's not impossible, but we have not used this. But that might be actually a good idea if we can implement it, to sidestep computing the pre-computing the training set.
Okay. And my other question is, so you showed results for finite mass. How would you expect mass of 0 to impact performance? Because then the conditioning gets really bad.
Exactly. That's a good question. Most Monte Carlo simulations have problems dealing with having exact 0 modes. And most of the methods we're using, will have problems there. If you're only interested in, you can obviously always do the study by introducing some sort of infrared cutoff, or a little bit of a mass, and then taking the limit as the mass goes to 0. But everything with the estimators will be sensitive to the cost of actually implementing the estimator, will be sensitive to that gap. In particular, all the routes that I've taken here are based on a polynomial approximation, and the order of the polynomial approximation depends strongly on the spectrum of the operator that you want to study, and the closer you get to 0, the more terms you have to keep in your polynomial to get a good approximation of the square root or the nth root over the spectrum of the operator. So in principle, when you take that gap to 0, that cost blows up in your face.
Okay, I see. And
Julian, can I stop you a second and give Dan a chance to ask?
Yeah, I suspect he has the same question. So yeah, thanks a lot.
Okay.
Hey, thanks for the talk. Yeah, so you're using this stochastic determinant ratio estimator for sampling. So we were playing with this, and we managed to convince ourselves that it actually violates detailed balance in a very subtle way. So we looked into it and went back to the old Grady paper where he shows detailed balance. And he makes an assumption that it's sufficient to have an unbiased estimator of the transition probability, but it turns out that that's not actually sufficient, and you don't converge to the correct target distribution. And actually what you need for a correct sampling procedure is to do sort of separate pseudo-fermion draws for each determinant. The keyword is like pseudo-marginal MCMC. But I'm happy to elaborate on that or talk more about it offline. But
yeah, this is interesting. I mean, I think that I've seen the proof is sort of straightforward for what what Grady method, why is supposed to be exact. I'm not sure exactly what I'm missing, but these things can be subtle. So I would like to see this in more detail. Dan, thanks for pointing this out.
Yeah, I have some.
I mean, I've actually used this in a number of contexts, and I've at least to the level of precision that I've tested, and sometimes I actually pushed it quite hard. I didn't see any tension between the results produced by the Grady method or other methods. So but it might be that the whole bias is very, very subtle.
Yeah, I have some toy examples I can send over to you.
Thank you, please do.
Yeah, Gert, and then we go back to Julian, perhaps. I'll come to the front so you can see me. Actually, this slide is the question about.
How do I see you guys? Because I don't see anybody. I just see. Can I stop sharing my slides so I can see this? Okay, good. Now I can see people.
So yeah, so the question about calculating the determinant, that was the determinant in the exact theory, huh? So that
Yes.
is only needed for the reweighting or the correction step, so to speak.
Yeah, for the accept reject.
Yeah,
yes.
yeah. So it has nothing to do, in principle, with the RBM construction that you use. It's just to make it exact, or not just. It's important, but it's to make it exact. So my question is about my question is about the RBM you use. So if I understand correctly, because it's restricted, it means that on the original lattice, all the nearest neighbor links are not there because they don't. But then you said you only use one node in the hidden lattice.
Yes.
So all the nearest neighbor interactions are erased, and they all talk with one node down there.
Yes, but there are. I completely agree with you, but there are different couplings from this one hidden node to every one node. Yeah.
Right. Yeah.
But of course, this is this was not meant to actually produce an RBM for the machine. It was more of a playground for trying to see if the estimators work. So we realized that this is this is a very simplistic machine, and we see it. That at large volumes, it actually you lose flexibility in the RBM. It doesn't really represent well the action.
So
I don't think it's our.
What's the reason to use one node then? Did you try more nodes in the hidden layer?
Oh, it's because we would need to implement. We tried a couple, 2-3 nodes, something like that. But beyond that, it seems that you really need, to make it really expressive, you really need a lot more technology than we had coded up. We didn't, we just did this by hand. We didn't use any kind of high performance package or whatnot. It's more of a let's see if we can get the estimators to work in this context more than getting the RBM to really be expressive. We tried a few things, but we didn't really try to go at scale with this.
Okay, yeah, good. Interesting. Bye.
Hi, Gert. It's nice to see you.
Okay, so I see that Julian's question was overlapping with Dan's one. Julian, do you still have questions or are you okay?
No, it's all right. That's good.
Okay, excellent. Do we have any other question in the audience in Trento? And in the audience on Zoom? No, then if there are no further questions, we thank Andrei again for the nice talk.